Hey, Calculus, Mr. Florio, optimization day 2. There's only one example on this, so we're just going to do one, and then you guys will have some practice problems on it. So it shouldn't take too long. So take a minute to copy it down. The question says, a rectangle is inscribed in the region bounded by the x-axis and the curve y equals negative x squared plus 4. What are the dimensions of the rectangle with the largest area that can be inscribed in the region? It seems like a tricky question, but just keep going back to those rules or those steps that we talked about last time. So we're going to try to find out what we're trying to maximize. So in this case, we're going to try to maximize the area of a rectangle. The variables that we're going to need, generally you need length and width. We're going to need to write a primary equation. So it's going to look something along the lines of length times width. Maybe there'll be x's and y's involved. I use a secondary equation to write your primary equation, so we're going to need some sort of other equation that kind of bounds it, right? And if we're talking about area, it makes sense that you need a second equation. If I want the biggest possible area and there's no bounds, my length and width can get as big as I want. So I need something that kind of constrains how big it can get. And the problem told us that we have the x-axis and that curve, negative x squared plus 4. And then once we have that, then we use our calculus. Take the derivative, set it equal to 0, and all that good stuff. So it's a big question, but it's just going to come down to exactly that. Let me draw the situation first and see what's going on here. Negative x squared plus 4. That is a y-intercept of 4. 3, 4. And I mean, you could set it equal to 0 to find the x-intercept. It's going to be plus or minus 2. You can graph it however you want to graph it, but I'm only interested in really this part of the graph. It's parabola. And it's going to look something like that. So it's bounded by the x-axis and that curve. So I want to make a rectangle in this region right here. What's the biggest possible rectangle I can make in that region? You can make this guy here. Maybe you can make a guy right here. How big? We want to know what the dimensions are to make that as big as possible. So without loss of generality here, I'm just going to draw some rectangle. Just so we have an idea. I want this thing to get as big as possible. I don't really know where the x and y values, but that's what we want to find out. So I want to find out the height, which I'm going to call y, which is going to relate to the y-axis. And the width, using the symmetry of everything, I'm not going to call it x. I'm going to call that x. I'm not going to call the width x. Because when I'm looking at a plane, I can find these coordinates here, and this could be like an x, and this would be like in the negative x direction. So I'm just going to call that whole width 2x, and it's not going to cause any issues here. So the primary equation that I want to maximize is the area. So primary equation is area, and it's base times height. The base is 2x. The height is y. And now I have two variables here, and I need a secondary equation that kind of constrains what x and y can be. And that curve, that parabola, is exactly what it is. So my secondary equation tells me that I know it has to be bounded by this relationship. So just plug that in. So the primary equation is the area. It's 2x times y. And we know y can be written as negative x squared plus 4. So now calculus it. We're going to simplify, well, I guess we'll algebra it, and then take the derivative set equal to 0, find the critical points, and that'll tell us the values that maximizes this area, this equation, which represents the area of that rectangle. So that's going to be negative 2x cubed plus 8x. So if that's the function for the area, the derivative or the rate of change is going to be negative 8x squared plus 8. Just kidding. Negative 6x squared plus 8. So we're going to set that equal to 0. Okay. I'm going to add the 6x squared to both sides. So 6x squared equals 8. Divide both sides by 6. I got x squared equals 8 over 6, which is the same thing as 4 over 3. So x is going to be plus or minus the square root of 4 over 3. And we can look at negative x values here because we're on the plane. And I'm just looking for a location. The actual value of 2 times x when we get it is going to be a positive number. If we put that in a calculator, 4/3 by square root that, about 1.15. Yeah, about 1.155. Approximately plus or minus 1.55. Cool. So that's where our function is going to be max or minimized, and I'm going to plug to get the y value. I'm going to plug it in here. Y equals negative x squared plus 4. Because I'm squaring the input, I'm just going to put the square root of 4 over 3 in here. You could say plus or minus because it's really not going to matter. We're only going to get one value here. So when you either square it positive root 4 over 3 or negative root 4 over 3, either way, the squaring and the squaring is going to undo each other, and you can get a positive 4 over 3 plus 4, which is, that's a 1.3333 plus 4. It's going to be 4.33333, I think. So I did forget one thing. There's going to be a negative. That negative is going to carry over. So 4 is the same thing as 12/3. So 12 thirds minus 4/3 is 8/3. Or what's 8/3? About 2 2/3. Yeah. Or 2.66666 repeating. Okay, so let's answer the question. What are the dimensions of the rectangle with the largest area? The dimensions are, so the base would be 2x, so it would be 2 times 1.55. I'm just going to type it here so you guys see what I'm doing. 1.155. That's a 1.155. It's about 2.31 by the height, which is 8/3, or about 2.67. Which is the same thing as saying, 2 times the square root of 4 over 3 by 8/3. And if this was like in a book, this would be really, right, the square root of 4 over 3 is really 2 over root 3, and then you'd rationalize that. So that'd be 2 root 3 over 3. That would be the actual x value as the book would write it. And then if I doubled it, then it would just be 4 root 3 over 3. So that's what that piece would be. But this is fine right here. Those are the dimensions. And you can even find, like, what is this x value? We know x is root 3 over 4, comma 8/3. And this point here would be negative root 4 over 3, comma 8/3. So you can even find like the exact points, but these are the dimensions to maximize the area. It doesn't actually ask us to find the area, but you multiply those two numbers together, that would tell you what the area is. Anyways, that's it, guys. Have a great Wednesday. The assignment for today is going to be posted. Have a good one. And email me if you have questions.